All right, so we're going to start talking about circles today. So I just want to review with you review one term, introduce another. So first is a central angle. So yesterday that was part of your vocabulary review, and that was part of those problems down at the bottom. So we learned that a central angle has a vertex on the center of the circle, right? And then it opens up to this arc. So if this is 52 degrees, that means this arc has to be 52 degrees, right? That's part of that review yesterday? Yes. All right. The reverse is also true. You know the arc, you know the angle. After Christmas break, we're also going to study something called inscribed angles, where the vertex is on the circle versus in the center of the circle, and the legs are chords. We're going to spend a whole day just looking at inscribed angles, things that happen with those. Okay, but that'll be after break. All right, so let's jump in. We're going to go over 5 properties, 5 conjectures, and then we're just going to practice them. Okay, so we're going to talk about each one first, and then we're going to practice them. So here's our first conjecture. It says if 2 chords in the circle are congruent, then they determine 2 central angles that are congruent. So the blank there is congruent. So in our specific case here, we're saying if AB, segment AB is congruent to segment CD. If we have those 2 congruent segments, then that means that then angle 1 has to be congruent to angle 2. All right, so if we have congruent chords, then we have congruent angles. So let's think about why this is. We'll write a formal proof for it in a minute, but let's think about why this is. So we're given that AB is congruent to CD. The if part is our given. So we're given that AB is congruent to CD. What's the nice thing about radii in a circle? They're all the same length, right? So that means that AK, BK, CK, and GK are all the same length. So first of all, what kind of triangles did I just create? Isosceles triangles. Isosceles triangles. So because we're dealing with radii, we have isosceles triangles all the time in circles. Okay, that happens a lot. Okay, the other thing is, look at that triangle on the left and the triangle on the right. Why are they congruent? Because of side, side, side. So we actually just identified 2 congruent triangles because of side, side, side. So now, why would angle 1 be congruent to angle 2? CP, CTC. All right, so think about what we just did. We just did in just one example here, we've talked about isosceles triangles, we've talked about congruent triangles. We even brought back in the idea of central angles from chapter 1. Okay, so all of this starts coming together, which is what, again, makes it so cool. All right, so we're going to write this formal proof to show that angle 1 is congruent to angle 2. So I wrote our given there. Okay, so we have our given is circle K. Circle K with AB, segment AB congruent to segment CD. Now, this is this chapter here is where we really do need to bring back in the segment marks and the arc marks, because we have arcs and segments in the same circle that have the same name. So we really need the symbol above to distinguish which one we're talking about. All right, so there's my given. Now, we said that all the radii had to be congruent, right? The nice thing about circles with the radii is I need all 4 of those radii. I can actually just list them all in one row. So AK is congruent to BK, which is congruent to CK, which is congruent to DK. The nice thing about that is then I can mix and match however I want without having to write a whole bunch of congruency statements. So I took care of them all in one foul swoop. All right, so now I'll mark all those as being congruent. So do we have all of our pieces?
Yes.
Yep, it's a good combination. Oh wait, I forgot to write my reason here. Because all radii in a circle are congruent. So all radii in a circle are congruent. Yep. Like Hawaii. So all radii in a circle are congruent. All right, so now we can say our triangles are congruent. So let's say that our triangles are congruent. So I can say triangle AKB is congruent to triangle CKD because of side, side, side. Okay, now you could have also said DKC as long as K is in the middle there. Because keep in mind, all four of those parts are congruent, right? So it doesn't matter how I flip-flop an isosceles triangle because we have multiple legs that are all the same length. So there's a little bit of flexibility there. It's really, in this case, as long as the K's line up, you can't be wrong. All right, so we have side, side, side. So now angle 1 has to be congruent to angle 2 because of CP, CTC.
Why can't you just say that they're equal right at the start by saying this chord central angle is projection?
That's what we're proving. We're proving why that is the case.
So, but if we wanted to prove that they were equal in a different problem, we would just put CCAC.
You won't have to. And I wouldn't recognize that. All right. All right, so questions about that proof? All right, so here's our next conjecture then. Says if two chords in a circle are congruent, then their arcs are congruent. So this is very similar. So our two chords in our case. So if AB is the segment AB is congruent to segment CD, then we're saying that arc AB has to be congruent to arc CD. So if the chord is congruent, then the arcs have to be congruent. So let's talk about why that is. We're not going to write out the formal proof for this, but we are going to reason through it. Okay? So I'm giving you that AB is congruent to CD. We just proved that if those two segments are congruent, those two chords are congruent, then angle 1 had to be congruent to angle 2, right? We just proved that? Okay, now think about angle 1. The measure of angle 1 is equal to the measure of arc AB. That was that central angle measure, right? If this is 52, this has to be 52. Okay, so the measure of angle 1 is equal to the measure of arc AB. We can do the same thing for angle 2. So the measure of angle 2 is equal to the measure of, I just did angle arc. I don't know why I did that, sorry. I should have used the arc AB. I don't know why I did angle there, I'm sorry. So the measure of angle 2 is going to be equal to the measure of arc CD. Okay, now look, we can do a substitution here. If angle 1 is equal to AB, arc AB, angle 2 is equal to arc CD, we can just sub it in. So that's why the arc AB has to be congruent to arc CD. Is that okay? Logically, does that make sense? Like why that all happened?
Like they mark the same distance. Like if you put points.
Mm-hmm. Yes, so that's logic. Like it feels good. It feels right. This is mathematically why it happens. Yes, I agree with you. All right. Next one. Next one here says the perpendicular from the center of a circle to a chord is the bisector. It's the bisector of the chord. So go ahead and fill in the blank, and then we'll talk about what that means. The word is bisector. So it says the perpendicular from the center. So I have the perpendicular to a chord. The perpendicular is coming from the center, so it has to be perpendicular right here. If you have the perpendicular, it's going to cut the chord in half. It's going to bisect the chord. Okay, so if you have the perpendicular, it's going to bisect. Okay, so let's figure out why that is. Let's make another connection here. So I'm going to focus on this triangle right here. So focus on that yellow triangle right there. I just drew in the radii. Okay, because before I just had a chord, right? I drew in the radii so I can make it a shape that I recognize. So what shape is that? An isosceles triangle, right? Because these are radii, these are congruent. Okay, I want you to think back to those Finding Nemo notes. We were talking about isosceles triangles, and we said that the angle bisector of the vertex angle there was also an altitude and a median. Do you remember that? Okay, that's what's happening here. We have an altitude, so that altitude is also the median, or the bisector, is also then the angle bisector. Does that make sense? Like, it's just we didn't have all the parts of that triangle drawn in. This is not really, well, we ended up proving that this left triangle was congruent to this right triangle and talk about all those parts.
Yeah, I'm just talking about the circle. Since you have the 90 degrees and you can do like the other side.
Yes, they are congruent, yes. But we don't even have to work that hard because we've already done that for all isosceles triangles. Because it's an isosceles triangle, we can just go ahead and jump to that. All right, next one. The next one says, two congruent chords in a circle are equidistant. They're equidistant from the center of the circle. So in our specific case, they're saying if segment AB is congruent to segment CD, then KM is congruent to KN. So if those chords are congruent, they have to be the same distance away from the center. Which logically feels good because if that chord got closer it gets to that center, the longer it's going to be, right? Because the longest it could be is if it goes right through the center. The further away it gets smaller. So it feels good that if the chords are the same length, they have to be the exact same distance from the center. Okay, so let's talk about why it is mathematically. Okay, so I'm going to draw in our radii again. And we know that all the radii are congruent. All right, we talked about that already. And I said in our if statement, AB has to be congruent to CD. So we know this side has to be congruent to this side. So are you okay with the fact that we have two congruent triangles there? We have chords that are congruent, and then all the radii are congruent. So by side, 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 we have congruent triangles again, right? The big ones. Okay, so by CB, CTC, we have all the angles, right? Well, this here ends up being like an altitude. It's an altitude for the triangle. And that ends up being part of like the whole CP, okay? So because it's corresponding parts, we could go through and prove that too by marking like A is congruent to D. And we know now that it bisects, so we could say like AN is congruent to DN. and do a whole nother set of congruent triangles. But that altitude really just starts being a corresponding part again. Does that make sense? Algebraic or geometrically wide? All right, we've got one more. All right, last one. It says the perpendicular bisector of a chord passes through the center of the circle. So we're saying if we have a chord that's been bisected and we have a perpendicular, then it must go through the center. Okay, so we're starting with the perpendicular bisector. If you have a perpendicular bisector of a chord, that bisector has to go through the center of the circle. This is my favorite conjecture in the whole wide world. I said this is my favorite conjecture in the whole wide world. I'm so glad you asked. Thank you. Okay, so once upon a time, I bought my very first house. Okay, it's a couple of years out of college, a couple of years into teaching. I bought my very first house. Okay, my house was very old. It was built, as far as we can tell, between 1880 and 1890. Okay, so we have paperwork back to then. Has anybody ever lived in a really old house like that? Ever? You have? Okay, so you can be my backup on this. Old houses fall apart, and when they fall apart, it's big. Okay? For example, yeah, see. For example, one time I went to change a light bulb in my laundry room. I unscrew the light bulb, the whole light fixture falls out of the ceiling. Okay? So I'm trying to fix the light fixture because I've learned how to do this. When you live in an old house, you figure out how to do a lot of things on your own. Because otherwise, you just have to sell because it's so expensive. So anyways, I'm trying to fix the light fixture. The wiring is just crap. I'm like, oh no. I had to rewire my whole laundry room because I needed to change the light bulb. Okay? Like, you hang up a picture, the wall crumbles. I mean, like, all true stories. Okay? So, one day I was in my basement, and my basement was just a dugout basement. The ground was basically dirt. At some points they had poured some cement, but it was like dug out after the house was built, I think. And the sides of the house, or the foundation, is just flagstone. So literally rocks just stacked up. Okay, and it's old. Not a nice basement. I'm down there doing something, probably fixing something else, and I hear this big gush of water. Okay, no, that's not a good sign when you own a home. Just so you know. So I'm searching around. In old homes especially, well, in all homes, you have what's called a soil pipe that takes any kind of wastewater from your house, whether it be toilet, sink, tub, takes it into a big pipe, and it takes it out of your house into the city sewer system or your septic tank, whatever you have. Okay, so in my house, I had a soil pipe that is just a stack. So it's just one big soil pipe that goes on the second floor from the bathroom down to the first floor bathroom, down to the basement, and out of the house. When they built houses a long time ago, they wanted to have the bathrooms so that they are on top of each other, because then you just have a little pipe to get to the big soil pipe, and you just have one big soil pipe to take it out of your house. Okay, now you can have multiple places that things exit. You can have pipes all over the place. But back then, pipes weren't made out of plastic like they are now. They're made out of cast iron. So what happens when you mix cast iron and water? It rusts. It rusts. So this soil pipe that takes all wastewater out of my house has rusted to the point it's collapsed on itself. That's right. Good. Which means now I no longer have a bathroom in my house that I can use. No shower, no toilet, no sink. Now my kitchen was added on much later, so it actually had its own method out, to join into the main sewer system. So my kitchen sink was the only source of water in my house at this point. Sad news, I had to move in with my parents because I didn't have a bathroom anymore.
Wait, was the gush of water just all sewer water?
It sure was. Oh, yeah. Sure was. Sure was. My sister was upstairs on the second floor, flushed the toilet, and the whole thing. Oh, yeah. Okay, so we ended up having to dust the whole bathroom. Okay, both bathrooms, because again, they're stacked on top of each other. So the plumbing gets messed up on one, it really messes up all the way down. Okay. And if you're gonna gut a bathroom, like you just need to fix it all right. Otherwise, you're just gonna be tearing it apart again to fix it the next time. So we gut the bathrooms. I can stand on my second floor. I can see all the way to my basement. Like that's how gutted they are, like down to the studs. Replace all the wiring, replace all the pipes. So we're ready to lay down flooring so we can install toilets and that kind of stuff. So I don't know if you know much about toilets. However, so let's say let's say the base of your toilet looks something like this, right? Maybe, right? Okay, I'm not an artist, I'm a math teacher here. Okay, so the base of your toilet is somewhat of a long oval, okay? The entire weight of the toilet is held on the rim of the toilet here. Once you go inside a little bit, it's kind of domed upward. With the exception of, there is a hole that is fairly large compared to that circle. Okay, it's pretty big in there. That's where you hook up your soil pipe to get rid of all the waste. Okay, so like the soil pipe usually comes, it's through the floor joist, and it makes a 90-degree turn and goes up into your floor, and then you set your toilet on top of that, and there's a wax ring. It kind of looks like earwax. It's gross if you've never seen it. It looks like earwax. You set it on top of your floor, and it joins to the pipe, and you squish your toilet on top of it, and that wax ring is the only thing that keeps poop and pee and stuff from coming out of your toilet. Yeah, it's bad. It's not fun to think about. Like, it's weird. It just seems like there should be a better way, but nonetheless. Okay, so we have to lay down plywood on the floor so that we can then put the flooring on, put the toilet on, right? But the problem is you have to cut a hole in this big piece of plywood for that pipe to come up through. So I need a hole that is a little bit bigger than this, but smaller than the big oval on the outside. And you don't have a whole lot of wiggle room. Okay, because if I create, like, let's say my big hole is like this for my pipe to come up through, I've created weak points on a big stress point for the toilet, okay, which just stresses your floor overall and it creates wobbliness. And keep in mind, only a wax ring seals your toilet to that soil pipe. Okay, so you don't want to have a wobbly toilet. If you have a wobbly toilet, fix it fast. Okay, so you're wrong. So we got to figure out how do we cut this hole, of course, in the middle of the board. So I have to go to the store, I buy lipstick, because I clearly do not wear lipstick. Okay, so I take, on the top of the pipe that we have installed, I put lipstick around the top, lay the board down, stand it up, it's now on my board. Okay, so I can see where I need to cut it. Got that done. Keep in mind, I can't afford to pay someone to do my bathroom, so my dad is trying to do my bathroom. Okay, that's, we still talk too, it's amazing. Okay, so now we need to cut out this hole. So it's like cutting out a hole out of the middle of a piece of paper. Except in that piece of paper I could fold and like snip and cut over to it, right? Can't do that on a board. I don't want to cut over to it because that would create another weak point, right? So I got to figure out how to cut that hole out. So they make this thing called a hole saw. It kind of looks like a can of tuna, okay? But it has like little jagged teeth right here, and it goes on a drill. It goes on a drill, and there is a drill bit that sticks out the top.
Birthday cake.
Not quite.
Well, you said your toilet looked like an avocado.
It kind of does. That's weird. All right. So this hole saw, the way this works is that the drill bit has to hit the exact middle of the circle, because then it spins around and those teeth cut out your circle perfectly. But the drill bit has to be in the middle. And even if you're like 1/4 of an inch off and you try to like adjust it, it keeps pulling itself back to that hole you've already started. So you've got one shot. Okay? My dad is a worrier. Okay? My dad overanalyzes everything. Okay? Like my parents' TV went out. Okay, my parents aren't hurting for money. Like, they're retired, but they are okay. All right? They're not hurting for money, and they need to buy a new TV. And we're not talking like a big widescreen. We're talking like go to Walmart and pay like $120 for a TV. Okay, which they could do. Okay, like finance finance for that was not an issue. My dad took 2 weeks to research and buy a CD from Best Buy. Oh my God. Okay, so anyways, he's very researched in things to the point of driving the person crazy. So, and sometimes you just have to let him spin his wheels. Do you know people like that? Like, you're never going to talk them into anything. You just got to let them decide first if they don't know what they're doing, and then you can help them. Okay, so this is where we are. So like, well, I don't know how we're going to find the center of this circle, because if we get this wrong, it's going to be all messed up. I go, no, you can't. You can't, because then it would ruin the board. Because I might have to try a new board. I go,
2
got
toilets.
this, Dad. Yeah, I got this, Dad. I am a geometry teacher, right? I got this, Dad. I can do this. So what I did was I used this theorem.
Yes.
I used this theorem. So here's my big circle. This is the circle I need to cut out, right? I need to find the center. So I drew in. I literally went and got my compass and a ruler. Okay.
What did I say?
I did. I really did. So I got my compass and a ruler. I drew a chord, and I found the perpendicular bisector. So do you remember when we were doing construction, we opened our compass more than halfway, we swung the big R, swung it from the other end, drew in the perpendicular bisector?
Yeah.
Did that for my floor there, on my floor. So I found that one. Then I did it again. Drew in another chord, found the perpendicular bisector, drew it in. What do you know?
Did you draw
They
it with
have to go
lipstick
through the center. What's that?
Did you draw it with lipstick too?
I did not.
just-
I did not. I did a pencil, thank you. But that's how I found the center of my circle. I'm like, okay, Dad, that's the center. Like, I don't know. I go, Dad, this is what I do for a living. He's like, I don't know. I get it. I'm paying for the bathroom. I paid for this board. Worst case scenario, I go buy a new board. Like, please just drill it. Okay, at this point, it's been hours. Like, this is like a 5-minute job. Okay? Hours. I'm like, please, Dad, just try it. And so I convince him, okay, we can try it. Drill it out, lay it down, it's perfect. I'm like, see, Dad, you need to trust in me. He's like, well, yes, that college education finally paid off. Thank you so much. Like, I've been, supporting myself, living on my own, bought a house, but now it pays off.
These are the stories in the short stories in our homework. Like, this is it. You just lived one out.
Exactly. All of that. So absolutely 100% true. Like, there is no exaggeration on any of that. Like, I truly did use that to remodel my bathroom. And just so you know, it took me 11 months to remodel my bathroom. I lived with my parents for 11 months. All right. So every time I think of this, I think of this bathroom. This is the center stall at Cheddar's. Ladies.
It's so small.
Okay, so in this bathroom, they had some really poor mathematics and bad geometry here. This toilet is so off-center. I don't know if you can see the walls very well. If you sit on the toilet, like one arm is like this, and then you have like a football field on the other side. It's so awkward. Okay, so this is why geometry is important. Yes. Yeah.
You should work for a toilet company.
All right. All right. So what I want you to do today, what I'm going to do. I'm going to give you about 3 minutes here. I want you to look at these 2 problems. Okay? I'm going to give you 3 minutes. I want you to look at these 2 problems, and then we're going to go over. Then we'll do a couple more, and we're going to go over. So I want you to solve for any unknown if possible. So I'll give you a hint. It's not always possible to find everything.
Okay.
What's that? Yes. Yes. There you go. You're welcome.
I know that.
I don't think it's. Oh, it's 8. They're the same. It's 8. But is the other one possible? I don't think the other one's possible. I would kind of say, going up now. Well, not that one, this one. This is that one. Which one? This one? So think of it like this. So these are the same circle. Right? That one. These, right? So 100 goes over here, they're the same. And then these things and also have to be good.
No, mine don't like it.
It's 50 for 50. I said that. I want to open 16, so equals 16. Oh no, they're not. This is not the rate. This is right here.
All right, you have no conversation? All right, so let's talk about the first two. All right, so what I noticed here is that I end up with some congruent triangles from the standpoint of I have 4 radii here that are congruent, right? Because we have an isosceles triangle up here, if this angle is 50 degrees, this angle also has to be 50 degrees, right? So we talked about the isosceles triangle, it's an altitude, so it's an angle bisector. It's also a perpendicular bisector. So that half is 8, this has to be 8. Now, if this angle is 100 degrees and this angle is 100 degrees, well, congruent angles have congruent chords, which means x then has to be 16. Now, everybody wants to say that y is 16. You actually cannot find y. It's impossible to find y. Because the reason we don't know is because we don't know if this angle is 100 degrees or not. We just don't know enough. Okay, you know. All right, next one.
I know.
All right, the next one. We have a radius here that's intersecting a chord, and it ended up bisecting that chord. So because it bisected and it went through the center, we have a perpendicular. So we have a right angle there. So W is 90 degrees.
So we can't do one.
Nope.
Oh, W.
All right, we also cannot find V. We do not have enough information to find V. Okay, now that being said, if we, sometimes what you can do, because all radii in a circle are congruent, you could draw a radius anywhere you wanted to, right? Because it's the same length no matter where you draw it in the circle. So sometimes what happens is they'll tell you like this segment right here is 2. But then because of a right angle, I actually create a right triangle. And I could use Pythagorean theorem if I would have known this length here. So I could have done a squared plus b squared equals c squared in order to get my radius for my hypotenuse. I could not in this situation, but I just wanted to throw in there because there is one on your homework where you can redraw the radius and use Pythagorean theorem. Okay? All right. I'm going to give you about 2 minutes to do the next two. I feel like these are a little bit easier.
All of the outside parts have to equal 360. Yeah, because this is equal, so it means it's an isosceles, which means this is I can't remember. I always do this. I can't remember the specific conjecture, but I just know that they're equal. But I can't remember which one. I'm sure if I look back and find it. They're like these are
You
equal.
don't have to know the name.
Yeah, but these are equal.
Because all radii are.
Yeah, see, I didn't know that, but I did. I can just look at it.
There you go.
I guess it's second. Yeah. Oh, yeah. I know. There's something.
Hey, you're working hard.
No.
Okay, about another 30 seconds here.
What's next?
Yeah.
All the outside are equal 36. Wait, if there's no dot, you can't assume you're to the side. So like if just take away for C or for the second problem, take away the dot and you can't solve it because you don't know if that's a radii or not.
Oh wait, that's
Okay.
All right, so let's take a look at the first one here. So first I notice that I have two congruent chords. If I have two congruent chords, that means I have two congruent arcs. So W has to be 100 degrees. Okay, now up here towards the top, I end up having an isosceles triangle. Right? Again, because my radii, which means that my base angles have to be congruent. So I have 35 and 35, which then I can find my missing angle of my triangle. That has to be 110 degrees. If I know my central angle, then I know my arc has to be 110 degrees. Okay, all my arcs added up around the circle have to equal 360. So if I add up what I have 310. So 360 minus 310 gives me 50 degrees. All right, next one.
Wait,
Yep.
how do you figure that?
Which one, the 50? The 50 part? Okay, so if I add up all my arcs, I have 360 degrees. So I knew this was 100, I knew this is 110, this is 100. So that's 310 total. Take it from 360, you have 50 left. All right, next one. The next one, I'm going through the center. This radius is coming, well, part of the radius here is coming from the center. It's intersecting this chord and bisecting it, which means that it has to be perpendicular as well. So now I've created this small right isosceles triangle, which means Z and this other base angle have to be congruent, so it has to be 45 and 45. Good on that one? We're just going to do the next one together so we don't run out of time. All right, so for the next one here, I see I have a 66-degree arc. All my other arcs now are associated with a bunch of congruent chords. Right? So I know all the way around is 360 degrees. Take away the 66 I already know. That leaves me with 294 degrees. I have to split that 294 equally among those 6 congruent arcs. Is that okay? All right, so if I do that, I end up getting 49 degrees for every one of these. Okay, so W is 49. Now, if this arc here is 49, this central angle here has to be 49. So what kind of triangle is that? It's an isosceles triangles, which means I can solve for my base angles. So 180 minus 49, then divided by 2, gives me 65 and a half. Not a pretty number, but it is what it is. So 65 and a half for those two base angles. So y there is 65 and a half. So now let's solve for x. Let's solve for x next. I think the easiest way to look at that is if I divide it into more isosceles triangles. Now because this is 49, we know this measure, this part of x, right? So this would have to be 65 and a half because these are all going to be congruent triangles. Okay, now let's take a look at this unknown triangle here. Because we have a 66-degree arc, that means this central angle has to be 66 degrees. Then I can solve for my missing angle. So 180 minus 66 gives me what, 114. Right? Divide that by 2, we get 57 and 57. Which means x is made up of 65.5 plus 57. So that is 122.5. Does that make sense? Okay, so you can see already so much of what we've learned feeds into circles. Isosceles triangles, congruent triangles. We haven't gotten the parallel lines yet. That'll be in there. Quadrilaterals will be in there. All right, so I'm giving you, there are some options to learn. I'm sorry you didn't have as much time today as you usually have. I'm just starting. Do your best order to get done. Me too. We'll go over this first thing tomorrow.
Heartworm. She said heartworm. You're like,